Hi everyone, this is Aryan and I'll be presenting our work STPro, Spatial and Temporal Progressive Learning for Weakly Supervised Spatio-Temporal Video Grounding, which I will refer to as STVG going forward. This work is a joint collaboration between myself from BITS Pilani and Akash Kumar and Dr. Yogesh Singh Rawat from the CRCV lab at the University of Central Florida. STVG involves open-world free-form grounding, in which we are given a real-world untrimmed video. The user can input any caption with no structural limitations, and we must ground both the mentioned object as well as the subset of all frames in which the object is actually present as indicated by the query. In this example, though the man is present throughout the video, the actions in the caption indicate the referred temporal subset, while the phrase man in red tells us who to spatialize. Here are some more examples of STVG. On the left, we need to localize the dog, while on the right, we need to localize the man that performs a certain set of actions. Can't VLMs easily solve STVG? After all, it's just a combination of referring expression grounding, which they're already really good at, and basic action recognition. Multimodal data models are very good at object detection. In this example, it is able to ground all the actors with a relatively high confidence. However, the model fails to correctly ground the exact referral phrase. Here, blue is the prediction, while green indicates the ground truth. We can see that the trivial adaptation while showing promise lags behind state-of-the-art by 5% VIOU, indicating that VLMs are not designed for dense video tasks. We recognize two major bottlenecks. Since the tracker lacks phrase context, we end up grounding the entire actor presence in the video. Also, due to difficult visual scenes such as overlapping actors, the confidence score of detections in a tubelet has high variance, making tubelet selection difficult. To mitigate these issues, we adopt a new pipeline with a dedicated spatial and temporal grounding module. We first generate tubelet proposals using grounding dyno and a tracking module. We then introduce the temporal referral module TRM, which cross-attends the encoded video and query to produce a start and end timestamp prediction. We reject those tubelets which do not fall within the predicted temporal bounds and forward the remaining to the spatial referral module SRM, which cross-attends the detection level tubelet features and query features to select one tubelet which has the highest prediction score. We adopt a weakly supervised training methodology for SRM and TRM. But why weakly supervised? Fully supervised annotations of temporal boundaries and per frame detections are very expensive. Since our feature extractor is trained on a very large dataset and remains frozen, our extracted features are less biased. And once features are extracted, training the cross-attention modules is very inexpensive and can easily scale to large datasets. While we see a 5% VIOU increase on both the large dataset VID-STG as well as smaller dataset HC-STVG, these results are not satisfactory. An upper bound analysis performed on both the datasets using the same detections from grounding dyno indicates that our scores are nearly 20% of what they can actually be, indicating that there are some major limitations in our approach. What are these limitations? We find that TRM lacks action composition understanding. For this analysis, we first find TRM's original prediction given the complete caption. Next, we modify the caption by removing the last action from the sequence. That is, in this case, we drop the phrase "and looks at the man in red" while keeping the rest of the caption unchanged. Since the last action is removed, we expect that the temporal prediction will shift to the left. However, we find that the prediction actually shifts to the right. In fact, when we extend this similarly with first and last action removal to the entire dataset, we find an incorrect shift in more than 50% of samples. Why is this important and what's the solution? Since specific action sequences are sparse at training time, learning to compose actions improves new scenario generalization. Say we want to build up to this caption. In the first stage, we break down the caption into its individual actions. In the second stage, we create captions of two actions, puts down and turns and raises. We ensure not to skip over any actions. We repeat this until we train over the original captions. We also find that SRM's performance starts to deteriorate as the number of actors in the scene increases. In particular, SRM fails to ground not only the referred attribute, but also the right class. Since class and attribute combinations are sparse at training time, individual understanding of both leads to better new scenario generalization. We find that this challenge arises due to conflicting training signals in SRM at two levels. First, at a tubelet phrase level, SRM must learn to disambiguate both attribute and class in parallel. Instead, we propose soft label filtering to mitigate this. If the caption references women, we remove all man tubelets within SRM. As a result, SRM focuses explicitly on attribute disambiguation. Second, at a tubelet level, detection features have an influence of the background, which reduces the strength of the attribute training signal. To mitigate this, we propose congestion-guided sampling, which progressively trains SRM on scenes with actors in the same background to those scenes with actors in different backgrounds. So, do the curriculums really help? We individually analyze TRM and SRM on increasingly difficult scenarios and show that STPro performs better in more difficult scenarios. In summary, we proposed a simple novel adaptation of VLMs to STVG. Our work was the first to explore curriculum learning for making VLMs spatio-temporal context aware. Additionally, our approach is generalizable and easy to extend to large datasets. We will be at CVPR. Come visit our poster at Exhibit Hall D on 13 June. Also, scan the QR code to visit our project page. Thank you.